All right, we've been talking about logarithms. And we talk about the base, base 10 of log of x plus 2 plus 3, and the techniques of shifting, stretching, reflecting, and the general shape of what log graphs look like and stuff. But what we're getting into is basically log properties. All right, so let me describe to you guys the log properties you need to know. And all the properties, since you've had a nice weekend, and I know you guys studied all over the place on this stuff over the weekend. But so let's go ahead and talk about everything that I've discussed up to date about logarithms. This is your chapter 7.3 stuff. The first thing you need to know is the definition of log. When I have y equals the log base a of x, remember, the definition of log, you have the ability, if you don't like the log equation, is to rewrite it in what we call exponential form. And what I call the smiley face definition of log. You start with the base, you raise it to the other side, so it'll be a raised to the y, and it'll be equal to what you're taking the log of, x. These two guys are the exact same thing. Y equals the log base a of x is the same thing as a to the y is equal to x. Logarithms solve for exponents. That's why we study them and why they're so important. Other properties. When I have y equals the log base a of x, your base officially has to be a number greater than 0, and a is not 1. And mostly we've been focusing on bases that are bigger than 1. So these are the bases we've been really focusing on. But there's also the famous domain and range of log graphs. What is the domain and range? Domain. Log graphs, logs have restrictions like square roots and like division does and all this other good stuff. You can't divide by 0. You can't take the square root or an even root of a negative number. When it comes to logs, you cannot take the log of 0, nor can you take the log of negative numbers. You can only take the log of positive numbers. So your domain is whatever you're taking the log of, I'm taking the log of x here, must strictly be greater than 0. For that interval notation, that would be parentheses 0 to infinity. It can't be equal to 0. It's got to be strictly greater than 0. You can't take the log of negatives, nor can you take the log of zeros. The range, however, is always, when I deal with logs, is all real numbers. Always negative infinity to infinity. And if you go back and look at the graphs we were playing with in terms of these graphs, it goes straight down and it bowls and it goes up and over. And that up and over keeps on going to infinity. So it's negative infinity to positive infinity. But you will only graph one side of a log graph. There's a space over here that nothing gets graphed because your domain restriction. You can only take the log of positive numbers. Other log properties. We have lots of log properties. All right. The first one is the log base b of b is equal to 1. When you're taking the log of base b and you're taking of b, they'll cancel each other out. But remember, logarithms solve for exponents, but what is understood to be the exponent on this b right here is b raised to what power? First power. Anything to the first power is himself. So this log base b of b is actually equal to the power of 1. So the log base b of b cancels and you get 1. Another log property. I don't care what base you're dealing with, log base b of any base of 1 is always equal to 0. Why? Well, if you want to understand it, use the smiley face definition. Start with the base, b. Raise it to the other side, it equals what you're taking the log of. b raised to the 0 equals 1. That's one of our exponential properties. Of any base raised to the 0 power always equals what? 1. Therefore, in log form, log base b of 1 always equals 0. And as I just mentioned, log base b of 0, you can't take the log of 0, nor can you take the log of negative numbers. So the log base b of 0 does not exist. No solution there. But also, as I mentioned, logarithms and exponentials are inverses. Inverses cancel each other out. So here are two major formulas right here. The log base b of b raised to the x. B raised to the x is the exponential form. Let me blow it up so you guys can see this in the back here. All right. b raised to the x is the exponential form. When you take the log of that same base b, the log and the exponential are inverses. They cancel each other out, and you're just left with x. So the log of base b of b to the x is equal to x. So that means things like log base 2 of 2 to the x. The 2, base 2 and 2 to the x, they have the same base. They'll cancel each other out, and you're left with x. Doesn't matter what the base is. As long as the base on the log and the base on the exponential are the same, they'll cancel. And similarly, log b raised to the log, that's supposed to be base b of x, will be equal to x. So in other words, 2 raised to the log base 2 of x would also be equal to x. Exponentials and logs are inverses. They'll cancel each other out. So if I put the log in the exponent with the same base, they'll cancel each other out, and you're left with x. And one other thing that we already talked about is this idea of a log without a base. If you don't see a base on a log, what is the base understood to be? Base 10. And this guy's got a name. It is called the common log. And it is common, and the fact is when you see your log button on your calculator right here, it doesn't have a base on that log button. It is understood to be a base 10 log button. Does that make sense? That's your log base 10 button right there. So, to drill, to make sure you guys have got these log properties down, let's practice. On your mark, get set, go. What's the log base 2 of 2 going to be equal to? 1. That is actually property number 1. When the base on the log and the base of the function is the same, they'll cancel, and you're left with 1. What is the log base 6 of 1? I don't care what the base is. When you take the log of 1, what are you going to get? 0. These are nothing but properties. Turn the page. Number 3. What is the log base 4 of 4 to the x? X. When the base of the log and the base of the exponential are the same, they'll cancel and you're left with the exponent. That's just x. So, try this one. They're trying to mess you up on this one. What's the log base z of z raised to the x plus y? X plus y. Because the log on the base was z, the base of the exponential was z, they'll cancel each other out. What about this guy? What is the log, what is 8 raised to the log base 8 of 12y? 12y. That's one of our properties. When the base is the same as the exponential base log, a raised to the log base a of whatever x, you just get x out of it. So in this case, you're going to get 12y. And let's see if you guys know this one. What is the log of 10? Very good. What is the base on this log, even though we didn't write 1? 10. So this is the log of base 10 of 10. This was that first property. When the base on the log and the base of the exponential are the same, you get just the exponent, and it's understood to be the exponent of 1. The answer is 1. They'll cancel each other out. Does that make sense? Other log properties here. What we're ultimately trying to get you guys into is solving logarithmic equations. So, when I have an equation with a bunch of logs on it, here's the deal. If I can somehow combine like terms to get the logs of the same base here, get the one log of base on one side equals the log base of the other. If the logs are equal to each other, then what you're taking the log of have to be equal to each other. So this is going to be using some of our log properties. I'm going to come back to this example after I introduce some more log properties. What I really want to do is introduce some log properties. I'm going to come back to this guy in just a second. There are 2 logs that you guys want to be very familiar with in terms of your calculator, because we are going to be doing problems on the calculator and working these things through. And the first one is this. What log is this button right here? You see the LOG button on your calculator? What is it? Log base what? Log base 10. There is another log button on your calculator. And that other button on your calculator is an LN button. You will see the LN button located right there. You will notice that it's just below the log button. It's LN. It's a fancy log button, LN instead of LOG. This is LN, which stands for the natural log, and the natural log of x, by definition, is equal to the log base E of x. Remember that E number we talked about? E, which is 2.71828, and it keeps on going forever, decimal number here, this exponential number. You get to see that in a lot of real-world application problems of population growth, radioactive decay, compound continuous formulas, things like that. This E, 2.71828, well, we have a special log with that particular base, and that is called the LN, or natural log. Log del natural, some French thing here. Natural log is what this stands for, okay? So, let's rewrite the equivalent statement on this guy. So the first one is this. We never write log base E. What is log base E also known as? The natural log of 3z squared. This is what we're after. We don't write log base E. We write natural log of 3z squared. What about this one? Calculated. This is a property. What is the natural log of E going to be equal to? What's natural log of E? Well, remember, natural log is the same thing as the log base E of E. Well, when the base on your log and the base of what you're taking the log of are the same, what they're going to do to each other? Cancel. What are you left with? 1. The natural log of E is 1. Does that make sense? Well, you don't believe me, I'll prove it on the calculator. All right. The natural log button is located right here. I'm going to push it. Natural log. The E button, you want just E. They actually have an E button. It's right above the divide. You see that little E? It's blue. Second blue. The natural log of E. Let me put it down here so you guys can see it. According to my calculation, because the natural log is log base E of E, I should get 1. When I hit enter, guess what I get? 1. Get familiar with your calculator. We're going to do lots of calculator work on this stuff. All right. Now remember, I skipped over a problem because I need these properties to be able to do it. So I'm going to come back to that problem in just a second. All right. There are obviously lots of log properties you need to know. There are actually 7 log properties. All right? 7 log properties. I've only wrote down 3, and I've given you the other major 4 ones a few seconds ago. I'm going to put them all down for you guys. But there are 7 log properties you need to know. Now, here's the deal. Logarithms solve for exponents. They are the inverses of exponents. And as I mentioned to you guys before, when you guys have been playing with exponents, you've been playing with exponents since about the 4th or 5th grade. You've been playing with logs since about the junior or senior year in high school. So you guys don't have that much of a track record on logs, but you have a long track record on exponentials, exponents. What's your properties? Exponential property. When I have a to the m times a to the n, when I multiply and have like bases, what do I get to do with the exponents? I add them. Same idea with the log properties, but there's an equivalent log property for the inverse of that guy. When you have the log base b of m times n, that's equal to the log base b of m plus the log base b of n. Multiplication turns into addition. You don't get to distribute logs or anything like that. Multiplication, log base b of m times n is equal to the log base b of m plus the log base b of n. Well, if multiplication turns into addition, what do you think division is going to turn into? Subtraction. Log base b of m divided by n is equal to the log base b of m minus the log base b of n. So multiplication means you get to add logs of each term. Division means you get to subtract logs from each term. Your third major log property is this. It comes from the exponentials. If I have a raised to the m, then raised to the n, a power raised to another power, a to the m raised to the n, a power to a power, what do we get to do with the powers? Multiply. So, but remember, log solve for exponents. This is like an exponent. I got the log base b of m raised to the n power. But power to a power, I get to multiply. But to turn this into multiplication, the exponent n gets to go in front. So the log base b of m raised to the n is equal to n times the log base b of m. Powers get to go out front. That is a very, very important log property. They call it the product rule log property. But as I mentioned to you guys before, there are 7 properties of logs. Property number 4 was this guy. The log base b of 1 is equal to 0. Property number 5 of logs is the log base b of b is equal to 1. Property number 6, the log base b of b raised to the x. Exponentials and logarithms are inverses. They cancel. You're just left with x. And property number 7, b raised to the log base b of x. Even though the base is b, the exponential has got a log in it. They'll cancel. You're left with just x. These are the 7 log properties you need to know. You need to know the definition of log in case you ever get in trouble. Y equals the log base b of x implies that b raised to the y equals x, what I call the smiley face definition. And the other one is, well, of course, you got to know your calculator. The common log is log base 10 of x, and the natural log of x is log understood to be base e of x. So, the ultimate goal is for me to get to these equations. So I've skipped over one because I want to apply these properties here. But take a look at these guys first, because I want to get you guys really into the log properties. Property number 1, they want you to simplify or expand the following logarithms. Log base b of x times y quantity cubed. Order of operations, if I'm cleaning up logs, is I'm going to do order of operations first. If I have x times y to the 3rd power, under strict multiplication division, I get to distribute powers. So this would be equal to the log base b of x cubed times y cubed. Only multiplication division can I distribute powers. Adding or subtracting with something to a power, I have to full it out. But now, let's use my log properties. What is the operation between the x cubed and the y cubed? Multiplication. What does multiplication turn into? Addition. So this would be equal to the log base b of x cubed plus the log base b of y cubed. Multiplication turns into addition. But we're not done cleaning it up yet. Log property number 3. Where do powers get to go when you have a log in front of it? Log base b of m to the n, powers get to go out front. N times the log base b of m. So these powers get to go out front, and I get the answer 3 log base b of x plus 3 log base b of y. This is the simplified version of what log base b of x times y cubed is. Similarly, how would you expand or simplify the log base b of x times y cubed? Again, what is the operation between the x and the y cubed? Multiplication. What does multiplication turn into with log properties? Addition. This will be the log base b of x plus the log base b of y cubed. And then I look at it, and there's any other log property I can do to this problem to clean it up? One more. Where do powers get to go when you're taking the log of something to a power? Out front, at the coefficient in front of the log. Now, there's no exponent on the x, so just leave that term alone there. But the log base b, we have y cubed. Where does that 3 get to go? In front of its log. So this would be the log base b of x plus 3 log base b of y. And that would be my solution. We'll try to turn up the heat a little bit. Try this one. Log base b of x cubed times y divided by z squared. Look at the location. I've got strict multiplication division. I've got x cubed times y, so the times is on top, and this is division, z squared. When the multiplication is on top multiply on a fraction. When you multiply, log property says it turns into addition. Division turns into subtraction. So what is this going to clean up to be? This will be equal to the log base b of x cubed. On top is multiplication, that turns into addition. The log base b of y. But that division means I'm dividing. And so that z squared, division turns into subtraction, minus the log base b of z squared. But one more move to clean it up. Where do my powers, my exponents get to go if I'm cleaning up logs? In front of the logs. So this would be equal to 3 log base b of x plus the log base b of y minus 2 log base b of z. And this is my solution. Take a look next one. What is ln? Natural log. But it's a logarithm, so it still has the same properties. It's just understood to be a base e. Remember that. So, first things first. Logarithms solve for exponents, so I like to play with exponents when I'm dealing with logs. I don't do square roots. What's a square root when I want exponential properties here? Half a power. So this is equal to the natural log of e times x to the half a power. But whether it's a fraction or a whole number, it doesn't matter. Strict multiplication division, I can distribute the power. So cleaning it up, this would be the natural log of e to the 1/2 times x to the 1/2. Because it's multiplication or division raised to a power, I get to distribute the power. Now, this is the natural log, but it's a log of e to the 1/2 times x to the 1/2. Multiplication turns into what? Addition. So this would be equal to the natural log of e to the 1/2 plus the natural log of x to the 1/2. Now use your log properties to clean it up. What is the natural log of e to the 1/2? What is the base on a natural log? Understood to be, even though we don't write it down there, e. And I'll write them down there just for your benefit. That's a log base e. When you got the log that has the base, it's the same as the base of the exponential. My log property number 6 says when the log of the log with the base has the same base as the exponential, they'll cancel each other out and you get the exponent, x. So based upon that, what is the natural log of e to the 1/2? These guys will cancel out. Natural log and e's. Get this in your mind always. Natural log and e's cancel. So you're left with 1/2 plus, this is natural log of x squared. I'm sorry, x to the 1/2, excuse me. Natural log of x to the 1/2. Where does the 1/2 get to go when you got a log in front of it? Out in front of the log, that'll be 1/2 the natural log of x. This is the cleaned up version of the natural log of the square root of e times x. Does that make sense? All right? Turn page. Can we make them tougher? Sure. The natural log of x to the 4th times the square root of x squared plus 3 divided by x plus 3 to the 5th. First things first. There's a John property. Let me write you a John property. John property. The log base b of x plus or minus y does not equal the log base b of x plus or minus the log base b of y. You are not allowed to distribute a log. Does not equal. Bad. Do not do this. The log base b of x plus or minus y. You've got to have strict multiplication division so you can distribute powers. Addition, subtraction, they have to stay where they're at. Okay? So you can't touch this guy because it's addition or subtraction. Now, First things first, clean it up. I don't do square roots. What's a square root? It's to the 1/2 power. So this is equal to the natural log of x to the 4th times z squared plus 3 to the 1/2 power divided by x plus 3 to the 5th power. Does that make sense? Now, multiplication turns into addition, division turns into subtraction. So this would be equal to, in the numerator, we're multiplying. It's x to the 4th times z squared plus 3 to the 1/2 power. That multiplication turns into addition. So this would be the natural log, that's an x there, I don't know why I put a z there, sorry about that. I'm sorry, x. So, but nevertheless, it's x squared plus 3, but that multiplication turns into addition. This will be the natural log of x to the 4th plus the natural log of x squared plus 3 to the 1/2 power. But this is division. Division turns into subtraction. Minus the natural log of x plus 3 to the 5th. Well, I'm almost done except for these things that have powers. Where do powers get to go? In front of the logs. So this would be equal to 4 natural log of x plus 1/2, the natural log of x squared plus 3 minus 5 natural log of x plus 3. And this is my solution, and that is the best I can make it. But you understand, there are hard-headed individuals out there that will not follow my John property here. What does the John property say? You can't distribute logs. Log base b of x plus or minus y is not equal to log base b of x plus or minus log base b of y. You cannot distribute logs. But how many times have I seen people, the 1/2 the natural log of x squared plus 3 is clearly 1/2 the natural log of x squared plus 1/2 the natural log of 3 and try to distribute that natural log. You're not allowed to do that. Only multiplication turns into addition, division turns into subtraction. All right? So that is the best my answer can do. You cannot distribute logs. Now I'm trying to turn up the heat a little bit for you guys. Try this one. Log of 100 times x plus 3 divided by z, there's a z there, times x minus 4 cubed. All right. Again, expand these logs. And another way I would write this in terms of my directions would be rewrite in terms of multiple logs of single variables. Bust him up. I look at logs like Humpty Dumpty. You remember the old Humpty Dumpty story, right? Humpty Dumpty climbed up on a wall and then somebody shot him and busted into a billion pieces. That's your job. Take your baseball bat after this big Humpty Dumpty and bust him into a billion pieces. That's your job. Rewrite this big log in terms of multiple logs of single variables. Bust him up. So, pay attention. What is the base on this log here? Understood, even though we don't see it. Base 10. This is multiplication. Multiplication in the numerator turns into addition. This will be the log of 100 plus the log of x plus the log of x plus 3. Multiplication turns into addition. But watch what I'm doing. You see this guy right here, that big old bar right there? What do you call that? Division. Anything in the bottom means you're dividing by it. So we're dividing by z, and, most important, we're dividing by x minus 4 cubed. Division turns into subtraction. This would be minus the log of z minus the log of x minus 4 cubed. And I already know, wait a minute, shouldn't that be a plus right there? Well, you're looking locally and not globally. Listen to my words. You're right. You're multiplying z times x minus 4 cubed. But, listen up. That's locally you're multiplying. Where is the z located at? And where is the x minus 4 cubed located at? They are both in the denominator. When you're playing with fractions and you have terms in the denominator, denominator means you are dividing by them. And if you divide by them, division turns into subtraction. If you want to look at it your way, you'll just do it in multiple steps. You would put a parentheses around all this stuff because locally it would be addition, but then that minus would distribute to get back to where I started from. So basically look globally. If the terms are in the numerator and they're being multiplied, that will turn into addition. If the terms are in the denominator and you're multiplying them, but they're in the denominator means you're dividing by them, every term in the denominator will turn into a subtraction because you're dividing by these terms. Let's finish cleaning this up. Now, this is for your benefit. What is the log? What's understood based on this log? 10. But of 100. Well, log of base 10 of 100. What exactly is 100? Let's break it down. What times what is 100? 10 times 10, or 10 squared. So this will be the log base 10 of 10 squared. And when the base on the log and the base on the exponential are the same, they do what to each other? Cancel each other out, and what are you left with? 2. Because that log base 10 of 100, 100 is 10 squared, they'll cancel each other out, and you're left with the exponent 2. Plus the log of x, there's no power here, plus the log of x plus 3, there's no power, understood to be a power 1 there, so nothing to move out front, minus the log of z, there's no power there except understood to be 1. But wait a minute, there is a power here. What is the power on the log of x minus 4? It is what? Cubed, raised to third power. And where do powers get to go? Out front. Minus 3 log of x minus 4. And this is my solution. Remember, you can't distribute logs over addition or subtraction. This is the best answer can be. But as I mentioned to you guys about the Humpty Dumpty problem, in the first part, we were taking Humpty Dumpty and taking our baseball bat and busting him up into multiple pieces. One big log, we rewrote him in terms of multiple logs of single variables. And this one right here, look at the directions. They say, quote, write the following as a single logarithm. In other words, here's Humpty Dumpty in multiple pieces. What's your job to do now? Put him back together again. So, but to put him back together again, look at these log properties. Let me go back and find my log properties here because I want to emphasize this. So in these log properties, now we're going to put Humpty Dumpty back together again. We got multiple terms of logs and we want to combine them. So that means addition will turn back into multiplication and subtraction will turn back into division, and numbers in front of the logs go back to powers where they came from. But, most important, for you to be able to combine logs, addition or subtraction, what is the coefficient in front of the logs before you turn addition back into multiplication or subtraction back into division? The numbers in front of the logarithms have to be a 1 to combine logs. If you have a number in front of the log, you first have to put him back where he came from. The coefficients in front of logs go back into exponents. So, take a look at this guy. I want to combine logs. I got 3 times the log base b of z plus 4 times the log base b of x. Before I can combine these logs, I know multiplication turns back, addition. Addition turns back into multiplication. But before I can do that, the coefficient in front of the logs have to be 1. I got a 3 in front of the log. Where did this 3 come from, and how do I get him back to it? This would be equal to what? Log base b of z cubed, right? Plus, that 4 is a coefficient from the log. He must have come from the exponent on the x. So that'd be plus the log base b of x to the 4th. Now you've got understood coefficients of 1 in front of your logs. And also remember this, you can only combine like logs. So the logs have to have the exact same base. These do, they have base b here. And what does addition turn back into? Multiplication. So this will be 1 big log base b of, and just multiply your term, z cubed times x to the 4th. And this is my solution. Does that make sense? But remember, before you can combine logs, you've got to make sure the coefficient in front of the log go back into the exponents. Take a look at number 8 here. 1/2 log of x plus 2 minus the log of x. Well, it's understood that the log is base 10 on these logs because they didn't write a base. But before I can combine them, you're right. Subtraction turns back into division. But before I can do that, any coefficient in front of the log had to go back where he came from. That's a 1/2 in front of the log. So where does he go back to? The exponent. So this turns into the log of x plus 2 to the 1/2 power minus the log of x. Does that make sense? Now, subtraction turns into division. So this would be equal to 1 big log of x plus 2 to the 1/2 power divided by x. And you're taking the log of one big term there. And one last thing. Because I'm trying to prepare you guys for the cumulative final exam, and this is the kind of stuff they'll do to you guys on the cumulative final exam on a multiple choice question, they would clean it up one further step. What's a 1/2 power also known as? They would write it like this. Log of the square root of x plus 2 divided by x. This is how the quote back of the book would look. Does that make sense? Page. More Humpty Dumpty problems, so let's go after these guys. 3 times the log base 5 of z minus 1/2 log base 5 of z plus 2 plus 2 log base 5 of y. Combine logs. In other words, rewrite as a single logarithm is what you want to do. Simplify this. Now, remember this. Subtraction turns into division. Multiplication turns into addition, and vice versa. So, first things first. For you to be able to combine logs, if you have a coefficient in front of the log, you got to put him back where he came from. So this 3, this 1/2, and this 2 have to go back where they came from, which is exponents. So this would be equal to the log base 5 of z cubed minus the log base 5 of z plus 2 raised to the 1/2 power plus the log base 5 of y. All I did was squared, lost a 2 there, sorry, y squared. All I've done is taking my coefficients in front of the logs and putting back into the exponents. Now this bothers a lot of students, but we don't care about order when it comes to these guys. Addition turns into multiplication. Listen to my words. Addition turns into multiplication, and multiplication always shows up in the numerator. Subtraction turns into division, and division shows up in the denominator. It doesn't matter about order. So combining to one big log, this will be 1 big log base 5 of, and here we go. You see that z cubed? It is understood, even though we don't see a plus in front of it, it's positive. So the z cubed shows up on top. You see that minus right there? Minus turns into division, so the z plus 2 to the 1/2 power will show up in the denominator. But this is back to being plus again. Plus turns back into multiplication, and multiplication shows up where? In the numerator. So the y squared will be back in the numerator. If it's addition, it'll be in the numerator. If it's subtraction, it'll be in the denominator. That's the pattern. And of course, to get that back at the book, look for the multiple choice answers on your test or whatever, you get the log base 5 of z cubed y squared divided by, what's a 1/2 power also known as? Square root of z plus 2. Does that make sense? And remember, order doesn't matter. Let's clean up this next guy. Okay. Oh, question. Sorry. Yes, ma'am. What is the operation in front of that y squared? What is that? Plus. And plus turns back into addition, turns back into multiplication. And multiplication shows up in the numerator. So regardless of the order, I can rearrange them. A plus B and B plus A, it doesn't matter, they're the same thing. It's the sign in front of it tells you where it's going to go. If it's a minus, it'll go in the denominator. If it's a plus, it'll go into the numerator. Watch that about this problem here. It doesn't matter about the order, it matters about the sign that's in front of this guy. Now combine these guys. You'll notice on this particular log, I got log base 10 all the way down the line. I got the log of 12 plus the log of x squared minus 81 minus the log of 3 minus the log of x minus 9. And I want you to simplify this one. So let's see what we get here. So what is the coefficient in front of each one of these logs? What's the numbers in front of each one of these logs? 1. Even though we don't see it, they're understood to be 1. So there's no exponents to put anywhere. They're all going to be 1. So I just got to get it turned into one big log. Understood to be base 10. So I write one big log with a division mark. If it's positive term, that term will show up in the numerator. If it's a minus term, the minus means division. Division shows up in the denominator. What is understood to be the sign in front of this log right here? The log of 12, what is it? Positive. So where's that 12 going to go? On the top. That's a plus. A log of x squared minus 81. So where's that x squared minus 81 going to go? On the top. X squared minus 81. That's a minus log of 3. It's a minus, so where's that 3 going to go? On the bottom. And it's a minus log of x minus 9. So where's that x minus 9 going to go? On the bottom. Minus goes on bottom, plus goes on top. That's the pattern on logs. Addition turns into multiplication. Multiplication turns back into addition. Subtraction turns into division. Division turns back into subtraction. Clean it up, though. I need a parenthesis right there. Because they want you to clean this up. Well, you can clean this thing up. Now you got it inside parentheses. 3 goes into 12 how many times? 4 times. I can just cancel that out and make it a 4 up there. Keep going. X squared minus 81. You should know how to factor that guy. That's like day 1 in this class. How does x squared minus 81 factor? So that would be log of 4 times, difference of squares, x plus 9 times x minus 9 divided by x minus 9. So what cleans up? What cancels? X minus 9 is canceled. So you get the solution cleaned up. It'll be log, understood to be base 10, of 4 times x plus 9. So you can do algebra on this stuff, but you want to do algebra when it's got the big division parentheses stuff there. Okay? So, before I forget, let me go back to this problem, because you needed your log properties to do this problem. All right. This is an equation, and this is where we're going to. We just introduced this concept in the beginning, but we put a bad example here, so I wanted to wait to do this example. All right. This is what I call a log type 2 equation. Logs on both sides of the equation. So I have here the log of x plus 2 minus the log of 4x plus 3 is equal to the log of 1 over x. I got logs on both sides of the equation. But we have a property that says when you got a log type 2 equation, and if you can combine logs to get it, the log base b of m is equal to the log base b of n. So in other words, I got the same logs on both sides. Log base b of m equals log base b of n. When you're going to be solving for some variable, what I do to one side of an equation, I can do to the other. I can cancel the log on one side, which means I have to cancel the log on the other. But because they're the same log, you can cancel them, and it just means what you're taking the log of have to be equal to each other. M equals n. So I'm going to use this property on this equation because I got logs on both sides. Now, I want to combine logs on this guy. So you're right, I went to chapter 7.4 because I needed those properties there. But what is the log of x plus 2 minus the log of 4x plus 3? What does subtraction turn into? Division. So you can combine logs. There are coefficients in front of the logs are understood to be 1, so that's good. So the subtraction turns into division. This will be the log of x plus 2 divided by 4x plus 3. It's equal to, and on this side I got the log of 1 over x. According to this property, what are the bases on these logs right here understood to be? 10. And when I have the same logs on both sides of an equation, and I'm trying to solve, what I do to one side, I can do the other. So I can cancel the log on one side, which means I can cancel the log on the other. So you can get rid of the logs. What I do to one side, I do to the other. And what does that mean I'm going to have? X plus 2 over 4x plus 3 is going to be equal to 1 over x. Now this should scare you because we're now solving logarithmic equations. But all I did was combine logs. That's kind of what all these log properties are about. But here's my question for you guys. How would you solve for x on this thing? X plus 2 divided by 4x plus 3 equals 1 over x. How are you going to solve for x? What would you do? All right, common denominator. What would your common denominator be? 4x plus 3 times x. You basically, to get a common denominator with variables, you just put the two denominators together to get the common denominator, right? So I'm going to multiply both sides by x times 4x plus 3. When I multiply on the left, the 4x plus 3's cancel. You with me? And I'm left with x times the numerator, x plus 2, equals. On the right side, I got 1 over x times my common denominator, x times 4x plus 3. And you notice the x's cancel. I'm left with 1 times 4x plus 3. The end result of this, when you have a fraction equals a fraction, and you multiply by your common denominator, you may also know this as cross multiplication. This denominator shows up over here. This denominator shows up over here when you multiply by your common denominator. You cross multiply. Now, solve for x. How am I going to solve for x? I'm going to distribute and scare you. I'm going to distribute the x. That gives me x squared plus 2x is equal to, distribute the 1, I got 4x plus 3. What did my equation just turn into? A quadratic. I can hide anything inside of a logarithmic equation, and you don't know what it is until you combine logs, get rid of the logs, and then basically then solve for x. How do you solve a quadratic? You always set these equations equal to your favorite number, which is 0. I'm going to subtract 4x and subtract 3 from both sides. Minus 4x minus 3. This is going to give me, running it this way, x squared, combine like terms. What is 2x minus 4x? Negative 2x minus 3 equals 0 because everything on this side cancels. Now you've got a quadratic equal to 0. You hope and pray, no guarantees on this one though, you hope and pray it factors. Does x squared minus 2x minus 3 factor? How does it factor? Very good. X minus 3 times x plus 1 equals 0. And then when you set a quadratic equal to 0, you set each factor equal to 0. X minus 3 equals 0, or x plus 1 equals 0. I'm sorry, x plus 1 equals 0. What do you get for x? X is equal to 3, or x is equal to what? Negative 1. And those are my solutions, right? Wrong. Here's the problem with logarithmic equations. So I'm setting you guys up for the next section, actually. Here's the problem with logarithmic equations. You got domain restrictions. You're not allowed to take the log of what kind of numbers? Negative numbers, nor 0. So any kind of log equation, you got to check your answer. Not that we didn't do everything absolutely right, but you have to check your answer. And you're not checking to make sure it's right. You're checking to make sure you don't violate a rule of mathematics, which is a log property, taking the log of a negative number. So let's plug in 3 first. And go back to the original equation. What's 3 plus 2? 5, nice and positive. I like him. What is 4 times 3 plus 3? 4 times 3 is 12, plus 3 is 15. It's nice and positive, that's all I care about. What's 1 over 3? Nice and positive. So as long as it's positive, this is your answer. X equals 3. Yes, ma'am?
I wonder what you did like with the cross multiplying like before you got the bucket.
Okay, anytime you got a fraction, x plus 2 divided by 4x plus 3 equals 1 over x, you either, what we call, multiply by your common denominator, which is x times 4x plus 3, and what happens is the 4x plus 3 is on one side, so the x on this side shows up over here as x times the numerator x plus 2, is equal to, here when you multiply by your common denominator, the x's cancel, you're left with the numerator 1 times the other denominator, 4x plus 3. And that officially is called, if you want the fast version, is cross multiply, because anytime you multiply a fraction equals a fraction by your common denominator, this denominator shows up in the numerator over here, and this denominator shows up in the numerator over here. It's called cross multiply. But wait a minute, I'm not done with this equation here. Now you've got to check x equals -1. Plug it into the original equation. Well, what is -1 plus 2? 1. That's nice and positive. That works. Go for the next one. What is 4 times -1 plus 3? Now, 4 times -1 is -4 plus 3 is -1. I'm not allowed to take the log of a negative number. And this is what I'm checking for. When I plugged in -1, that became -1 here. And I can't take the log of a negative number. If, let's say for example, that was an x squared on this thing. -1 squared would have been +1 times 4 would have been 4 plus 3. It still would have been positive. And then I could have had negative numbers in my answer, as long as when I plug it in, I'm taking the log of positive numbers. But when I plugged in -1 in here, it became negative. That means that if just one term is negative, get rid of it. So the only answer is what? X equals 3. Now, which means every time you do a logarithmic equation, you've got to check your answers. And you're not checking to make sure they're right. You're checking to make sure there's only, you're taking log of only positive numbers. But listen to me and listen good. This is where most students are going to screw this kind of problem up. They'll do the math right, and they'll circle their answers. And let me tell you, this is going to be a multiple choice question. A, x equals 3. B, x equals -1. C, x equals 3 and x equals -1. D, x equals 14, and E, no solution. Making up stuff. All right? You'd be amazed how many people put C because that's what they got. X equals 3 and x equals -1. But when you check -1, you can't take the log of a negative number, so that's what we call an extraneous solution. The only answer was A, x equals 3. Don't forget on logs to check your answers. And you're not checking to make sure your math is right. You're checking to make sure you don't violate a rule of math about taking the log of negative numbers. Does that make sense? So we're going to have a whole section on playing with logarithmic solutions here, solving equations. But before we get into that, there is one more thing we want to talk to you guys about. And that is one more formula, as if you don't have enough formulas to memorize. This is how to use your calculator. Now, if you've got the new TI-84, with the new operating system, they have a button for logs, which they recently just put in there. But in the old days, as in about a year ago, there's only 2 log buttons on most calculators. There is the common log and the natural log. That's it. And the reason for that is you don't actually have to need any other log buttons on it, because you have a formula called the change of base. It's called the change of base formula. And that's what this guy is. And it's nothing but a calculator formula. This is used for calculators. If I wanted to calculate, aka convert to a decimal on my calculator, the log base b of m, basically you can do what we call the change of base formula. So the log base b of m would be equal to the log base a of m divided by the log base a of b. You choose a. You choose the base, whatever you want to convert to. So in terms of changing base, if I have the log base b of m, that's equal to the log base a of m divided by the log base a of b, where I choose a. But if I'm using my calculator, there's only 2 bases I'm going to choose, because there's only 2 log buttons I have. What are the 2 log buttons I have? Common log and natural log. So that's why we wrote it like this. So if you want to convert this over, log base b of m would be equal to the log base 10 of m over the log base 10 of b. Or you could use the natural log. Natural log of m divided by the natural log of b. It's the log of what you're taking the log of divided by the log of the original base. It's a calculator problem. So use your calculator, notice directions, to find what's the log base 8 of 17? Well, it's up to you. I'm going to convert using my change of base formula. Do I want to use common logs or natural logs? Personally, it doesn't matter. This would be equal to, you always take the log of the original, what you're taking the log of, which is 17, divided by the log of the original base is 8. I'm going to put that on my calculator and show you. This will be log of 17 divided by the log of 8. Does that make sense? It's just a formula. You take the log of the original function divided by the log of the original base. What do I get? I get the decimal 1.362487614. 1.362487614. But personally, some people like the natural log better. Fine. Take the natural log of 17 and divide it by the natural log of that original base. As long as you use the same log type, log of the original number over the log of the base, you get the same number. Does that make sense? What does this number mean? So I have the log base 8 of 17 equals 1.362487614. What does it mean? What does this number 1.362 really mean to you guys? It means this. If you don't like logs, rewrite it and you'll understand what the meaning is. What is the base on this log? 8 raised to this power. 8 raised to the 1.362487614 will be equal to what you're taking the log of, 17. You just discovered what weird number I have to raise 8 to be able to get 17. And you don't believe me, watch. 8 raised to the 1.362487614. What does the calculator, let me slide up, you guys can see this. What does the calculator say I'm going to get? Okay, computer error here with the 0.0001. What do I get? 17, but it is a computer, so rounding off issues there, but there it is. It's pretty much 17. That's what logs do. They solve for exponents. All right? So, do another one. You understand, as long as you know the change of base formula, it's free points. I want you to calculate for me what the log base 5 of 15 is. In other words, 5 raised to what number is going to be equal to 15? Well, to calculate the log base 5 of 15, I'm going to use the change of base formula. Choose my calculator. This will be the log of the original function over the log of the original base, or I could use the natural log of the original function over the natural log of the original base. And tell me what you get. When I did it on my calculator, I get, base is 5, I get 1.682606194. Double check me, it's a calculator problem. Does that make sense? Now, I want to show you guys something or other if I can find it. I'm looking for it on my calculator here. All right. You'll see why I'm doing it so slowly here. L. All right. See if I can remember this one. All right. I have the new operating system on the TI-84, which most of you guys have. So there is a special button on the calculator for the log of any base. Okay? If you'll notice, there is a catalog button on it. You see the catalog? It's in blue on mine, so I'm going to hit second catalog. and it tells you what everything in the memory of the calculator is. I want you to scroll down until you get to the L's. I think you can do alpha L if I really want to. Alpha L, L. There we go, alpha L. So it takes me to the L's. Scroll down and look for log, and you'll see there's the natural log regression, that's something else, log. And then you see that one special one. You see it? They stuck it in there. It's under the catalog. Log base. That's a program for this thing right here. And only the new operating systems have this. If I hit enter, you'll notice it pops up like this. So, I want to do this problem here. What was it? Log base 8 of 17. So if you know where this program is, you don't have to memorize this formula if your calculator has the program for it. But it tells you what the answer is. So the new operating systems on the TD4 put in this change of base program already for you guys. It's called log base. I'll let you know about it. Okay? All right. So here we go. Solving a variable in the exponent. So, remember, logarithms solve for exponents. So, again, this is the kind of problem I can guarantee you're going to see on your final exam. Therefore, you're going to see on your next test. Now, all we're doing is manipulating an equation. I have an equation, r equals 25e to the 38 times x. Okay? Your mission, I want you to solve for x. So we're now talking about solving equations. We've been talking a little bit about log equations, and we'll get back to that. Now we're talking about solving exponential equations. The variable is located in the exponent of an e. The first thing you want to do, listen to my words in practice, get the term with the variable by itself. So, where's the variable located at? It's the exponent on the e. So what's my first move? I got to get that e by himself. So I got to get rid of that times 25. What gets rid of times 25? Divide both sides by 25. Here it'll cancel. That leaves me with r divided by 25 is equal to e raised to the 38x. Now, logarithms solve for exponents. Once you get that exponent by himself, you want to take a log of it. But what do I have in this problem? An e. What kills off e's and brings down exponents? Not just any log, natural log, log base e. So anytime I've got an e in the problem, I want to use the natural log. Does that make sense? So now my next step would be take the natural log of both sides. So the natural log of r divided by 25 would be the natural log of e raised to the 38x. But natural log and e's do what to each other? Cancel. That gives you the natural log of r divided by 25 is equal to just the exponent 38x. And now solve for x. What gets rid of that times 38? Divide by 38. This gives me x is equal to the natural log of r divided by 25 divided by 38. And that is my solution. Look at the next one. Same idea. Y is equal to 8 times e to the t times x. Again, your mission is to solve for x. So when the variable is in the exponent of an e, get that term with the e in it by himself. So what's my first move on this problem? Divide by 8. Get the e by himself. So I'm going to divide by 8 on both sides. That gives me y divided by 8 is equal to, that cancels, e to the t times x. We're solving for x in the exponent. Now the x is in the exponent of an e, so I need to kill off an e. What kills off e's? Natural log. So take the natural log of both sides. The natural log of y divided by 8 is equal to the natural log of e to the t times x. And natural log and e's cancel. Leaving you with the natural log of y divided by 8 is equal to t times x. Now solve for x. What am I going to do to solve for x? Divide by t. T is just some kind of number constant. Divide by t And that gives you the answer. X is equal to the natural log of y divided by 8 divided by t. All right? So, how can they mess you up? They're going to bring back some problems from your past. We know the future and current values are trying to solve the interest rate or time it takes for our principal to reach a certain value. The variable will be in the exponent. So, take a look at this guy. We're solving for exponents. How many years will it take an investment of $10,000 to reach $12,214 if it's invested at an interest rate of 5% compounded continuously? We got to memorize our formulas. What is the formula for compounded continuously? A equals PE to the RT. Pure memorization. Compounded continuously. Okay? Compounded continuously. A equals PERT. Now, read through your problem and type in your numbers here. You invested $10,000. What's that? That's your principal, P, $10,000. You reached $12,214. How much? What is that? A, the amount in the account, $12,214. Your investment interest rate was 5%. That's R. But remember, percentages for people who can't do math. What is 5%? 0.05. And your mission is to find time. How long will it take you, if you got $10,000, you put in an account with paying 5% interest, to actually reach $12,214? Well, let's find out. Plug in A is $12,214 equals your principal, $10,000, E to the interest rate, 0.05 times T. You notice your mission is to solve for T. It's located in the variable of your exponent E. What's your first move to solve for the variable T? You got to get that E by himself because that's got the variable in it. Your first move is divide by 10,000. When I divide by 10,000, 12,214 divided by 10,000 is 1.2214 equals E to the 0.05 T. What's your next move? To get rid of the E and bring down that exponent. Take the natural log of both sides. Natural log of these cancel. So I'm left with the natural log of 1.2214 equals the 0.05 T. And what's your last move to solve for T? Divide both sides by 0.05. This cancels, and that leaves you with T equals, and I'm going to type it on my calculator. Natural log of 1.2214, close parentheses, divided by 0.05. And don't forget to close the parentheses on your log, because the 0.05 is divided by, not inside the log. How long will it take? 3.999954836. What is time measured in when you invest? Years. So pretty much, because of rounding error, how long will it take? 4 years. And that would be the multiple choice answer you would see. All right, I got one more minute. Wait a minute. Let's finish this last problem, and then we're finished with section 4.3. Here's your last one. How many years will it take an investment to double if its interest rate is invested at 3.5% interest compounded continuously? This is one they're definitely going to stick on your final exam. Compounded continuously is, again, the PERT formula. But here's your problem. All they gave you was the interest rate, 3.5%, which is 0.035. But here's the deal. If P is your principal, whatever money you got, what is the amount you're going to get back if you double it? That's the trick right there. Double it. Double the amount of money. If you started out with $10,000, you double it, what do you get? $20,000. If you started out with P amount of money and you double it, what would you get? 2P. That's the trick right there. The doubling amount would be 2P. Plugging it in, this would be 2P is equal to P e to the 0.035T. To double the amount, A has to be the initial amount. You think I got too many variables here, but solve for T and look what happens. When you solve for t, what is your first move? What are you going to do first? Divide by p on both sides to get the e by himself. And when you do, what happens to the p's? They cancel out and you're left with 2 equals e to the 0.035t. Now what gets rid of that e? Take natural log of both sides. Natural log and e's cancel. So the natural log of 2 is equal to 0.035t. And your last move to solve for t? Divide by 0.035. So if you're talking about you got a 3.5% investment account here, how long would it take your money to double? It will be the natural log of 2 divided by 0.035. How long? 19.804200516 what? Years. Pretty much with low interest rate, it's going to take you a long time to double your money, almost 20 years. Study this stuff and have a happy Thanksgiving. I'll see you guys when you come back. And look very closely. You'll be seeing something very soon about a homework set being posted and stuff. It may be just when we get back. So look for it then. I'll see you guys on Monday.